an imaginary unit because in order to solve all quadratic equations, we need to know about this little thing called I, okay? So this is note that this is a definition. It's just like if you don't know what a word is, you look it up in the dictionary and it's defined. So then hopefully you can use it. Similarly with I. It's a very interesting historical thing if you're interested in knowing a little bit about where these symbols come from and the people that first came up with I, the mathematicians, and how they discovered it. It's always interesting to sometimes have a historical sense of these things. Unfortunately, with our limited time today, I can't quite go into all that. But I is defined to equal the square root of -1. Now, up until this point, in the class, we've always said we can't define the square root of a negative number, and that's because we've only operated with real numbers. We're going to now expand our real number set, and once we do that, we'll get there in a minute. We now have numbers that can represent square roots of negative numbers. So all you need to know is that I is defined to be the square root of -1. So now, if you have any positive number k, notice k is positive. So if that's out in front of it, it's going to automatically make it negative. The way you evaluate the square root of any negative number is to pull out the -1 that's in front of k. You can use your product rule here. Pull out the -1 and then leave k as it is, a square root of k. Now, if k is a perfect square like 4, square root of 4 you could call 2. And no, we don't know what k is, so we're going to leave it as a square root of k, but we know square root of -1 is defined to be I. So notice, anytime k is not a perfect square and it stays under the radical like that, the I always goes in front. So if we had a situation like this, this is how we prefer to write it. And the reason is, if you put the I on the other side, it's not clear if it's under the radical or not. So whenever k, the square root of k, is an irrational number, I goes in front of it, okay? If k is like this, if k is 4, then we tend to put the I after the real number 2, the rational number. Okay? Doesn't matter, it's just this is really the preferred way of writing it. So let's do a couple of these really quickly, these square roots of negative numbers. So when you look at this first one, you say, okay, 49 is a perfect square. So this is the square root, and you don't have to do all these steps. I'm just showing it to you. Square root of -1 is I. Square root of 49 is 7. You can either write it like that, or you could say 7I. Okay, either one. Any questions on that one? So we're just making the square root of the -1, the number I. Now 8 is not a perfect square. This takes a little more work. Okay, so you might think that this is all you have to do, because 8 is not a perfect square. However, you can simplify the square root of 8 a little more, because the square root of 8 has a factor that is a perfect square. It has the factor 4. You can write square root of 8 as square root of 4 times square root of 2, because 4 times 2 is 8. And notice square root of 4 is a perfect square, so you can write that as 2, but square root of 2 is irrational. So this is I times 2 square roots of 2. And like I say, generally, we put the real number first, then we write our I, and then we have square root of 2. So sometimes when you get these radicals where you're not a perfect square, but you're not you have a factor that's a perfect square, it can be simplified further. So if you left it like this versus like this, you'd lose maybe a point, if you didn't fully simplify it. So this is the kind, you did a lot of these in like Math 106, 096 along the way. Okay, so if you need a little practice with those, just take some numbers, like take some perfect squares like 9. Say 9 times 3 is 27. So 27 isn't a perfect square, but how could I write it as two radicals where one of them is a perfect square? Can someone give me two radicals I multiply to get 27 where one of those radicals represents 9 and 3, right? So you simplify this one, square root of 9, 3, and you got an irrational square root of 3 left. So you can simplify that to be 3 square roots of 3. Okay. So if you run across a couple of these on your homework and you put in I square root of 8 and you don't get the correct answer, it's just because they want you to simplify it. Okay. Now I square you're going to be using quite a bit in your multiplication. So I is defined to be the square root of -1. When you square both sides, you get I square on the left. And what happens when you square a square root? They undo each other, right? And you just get -1. So for our purposes, what we're going to use in terms of our operations with I, you need to know I is the square root of -1. And every time you see an I square, you can replace it with the number -1. Okay, so every time we see I square, that's what you replace it with is -1. So these are the two most useful definitions that you need. You can do I cubed and I to the fourth and I to any power, but those are the two that we really need for today. Any questions on these three problems before we move along? I know some of you had already worked some of these out. So this, my arrows are off here. This is just a definition of our new number set. Complex numbers are made up of real numbers and imaginary numbers. And the two, so the arrow should be pointing to 2. A complex number has this form, A plus BI, where A and B are real numbers and I is an imaginary unit. So if you have a number like this, 2 plus 5i, that's called an imaginary number, a complex number. 2 is the real part, 5 is the imaginary part. Both 2 and 5 are real numbers, but we call 5 the imaginary part. 3, it can also be 3, take away 4i. Now notice, every real number in the world is also a complex number because all we have to do is put a 0 where B is. And once we put a 0 where B is, you have your real number. Okay? If you have A as a real number, then this is what we call a pure imaginary number, where you just have the BI part. That's pure imaginary. I will never ask you to define those. It's just so that you have some of the language. So if you put all of your real numbers together, which we know and love so well, along with these new imaginary numbers, you get this set called the complex numbers. So to solve quadratic equations, we need to know how to represent complex numbers. So we pretty much add and subtract and multiply these types of numbers in exactly the same way we always do. You add, always in mathematics, you add and subtract like things. So if you just drop your parentheses here and you write out this expression with these 4 terms, you put together the ones that look like. So your real numbers here are 2 plus 1. You put those together and you get 3. And then you put together your imaginary pieces, terms, and you get 3i and 5i. 3 i's and 5 i's make 8 i's. So there you go. You're all done. 3 plus 8i. Just like you would do if the I was an x. Okay, if the I was an x, you'd have 2 plus 3x plus 1 plus 5x. You'd call it 8x's. Okay, so it's very similar. And similarly, when you subtract, you have to distribute the negative sign to both terms. So this becomes 2 plus 3i minus 1 minus 5i. So now you put your like terms together. 2 take away 1 is 1. And 3i take away 5i is 3 take away 5 is negative 2i. So that it shouldn't really be anything too new to you, because if you just imagine the I like a variable, even though it isn't a variable, you combine the like pieces just like you always do, the like terms. Where things get a little different is when you try to multiply two complex numbers. You use the same idea you always do. The first term times the first term is 2. Your outer term, 2 times 5i is 10i. Your middle term is 3i. And your last terms here are 3i times 5i, which is 15i squared. So this is where that little I squared comes in. So now you look at that and you say, okay, I got two like terms here right in the middle, and I'm going to put those two together. 2 plus 13i. 10i plus 3i is 13i. Do you mind raising your hand when you have a question, Mason? Thanks. Plus 15i squared. So at first blush, you might say, I've got a 2. That's different than an I term, and that's different than an I squared term, right? You might just say, I'm all done. This is like, when you think about it, could be like 15x squared plus 13x plus 2. That's how you're used to, that's the type of thing you're used to getting when you multiply two, say, binomials with x in them. But we're not quite done, because we can simplify this further, because whenever you see an I square, what do you get to replace it with? -1. So you replace the I square with a -1. So you get 15 times -1, because that's what I square is equal to. I square equals -1. And now you actually get to combine it one more time, because now you have 2 take away 15, and that's -13 plus 13i. So it works just like it normally does, except you just have to remember that I squared now can be simplified further. Any questions on how I got -13 plus 13i? You could also write this like this. You could change the order and write it this way if you prefer. It's up to you. All right, what do you notice about E? Does that remind you of anything, E? Anything at all, like special factors that we're used to looking at? Yeah. The difference of perfect squares. Let's do a little side note here. We notice that whenever we have x plus 2, x minus 2, or x plus 5, x minus 5, where your factors look almost identical except for your operation, one is addition and one is subtraction, we know we don't get a middle term. The middle term goes to 0. So you just square the first term, you square the last term, and you put a little minus sign in between. That's how it always works. Guess what? It doesn't change with complex numbers. Because if you look at this middle term right here, 2 times 3i is going to give you 6i. And the outer term is going to be 2 times -3i, which is -6i. And when you add that, you get a big fat 0. So if you recognize that your two complex numbers look almost identical except for one's addition and one is subtraction, then when you multiply them, you say, I'll square my 2, I square my 2, I square my 3i, and I put a subtraction between them. And then you simplify it. 2 square is 4. 3i square is 3i times 3i, which is 9i square. But you're not done, because you can replace I square with a -1, so that equals 4 plus 9, which is 13. That's a pretty complicated way to write the number 13. Okay, so this recognition here of these types of factors can really help you become more efficient. It doesn't mean you still can't do it out the long way with 4 multiplications. You'll still get here. It's just a recognition. Saves you a little bit of time. But I'm not going after speed here. If you just want to multiply the whole thing out, that's absolutely fine. If you're not confident in just going right to this type of notation, there's no problem with doing it all out. Okay? So these types of factors, no matter what they look like, whether they have x's in them or they're complex numbers, are called conjugates. That's what the term is that we refer to, conjugates. So in other words, oops. Something special happened in the last example. When we multiplied these two factors, we don't get any, we got a real number. There's no imaginary part. The imaginary part disappeared, and that's because these are conjugates of each other. So anytime you want to create a conjugate, you just change addition to subtraction or subtraction to addition. So what would be the conjugate of 2 plus 3i? What would be the conjugate of that? 2 take away 2 minus 3i, right? So those are called conjugates. If you want a real fancy name, conjugates of each other. All right, so all of this is critical for solving quadratic equations. Oh, let me just show you this one thing. So here's two complex numbers. And again, to do this, you would do a times a, you'd get a squared, take away b squared times I squared. The middle term just drops away. And the minute you change that I squared to a -1, what you end up getting is a squared plus b squared. Now, I don't know about you, but that's kind of exciting because up to this point in life, if you were given something like this and told to factor it, you've never been able to factor sums of perfect squares over real numbers. If you just have real numbers in your back pocket or your front pocket, you can't factor this. But now that we are working in the complex number realm, you know how to factor this. You can say this is x plus 2i times x minus 2i. Sums of any perfect squares always has factors that look like this. So if you had x squared plus 1, 1 is a perfect square. This is a sum. You just say x plus I, x minus I. X squared plus 100, x plus 10i times x minus 10i. So this represents these two conjugates, these two complex numbers that are conjugates of each other, represents the factorization of the sum of perfect squares. Okay. So you now have something else you can do that's more powerful because we have complex numbers. Okay, so what I'm going to do now, this is in your book, you'll read that. I want to get right into quadratic equations, and part of quadratic equations is recognizing what a quadratic equation is and how it differs from linear equations. So when we write a linear equation in one variable, two variables, we get to graph it and it has infinite number of solutions. When we have a linear equation with one variable, the highest power or exponent you see is 1. Even though we don't write it in there, it's understood there's a 1 there. So that's why we call these things first degree equations. The degree of a linear equation is the highest power you see, which is 1. A quadratic equation are called second degree equations because the highest exponent you see when you look all the way across your equation is 2. Even when it's in this either of these forms, this is called quadratic or second degree. So in general, this is what a quadratic equation looks like. This is the general form of a quadratic equation. When you put all the terms on one side of the equation and you set the right side equal to 0, a, b, and c are real numbers, and a cannot equal 0. Do you know why we say a cannot equal 0? When we define a quadratic, so like this is the definition of quadratic. So why do we say a can't be 0? Yep, Kaylin? Right, if a were 0, this would go away, and what kind of equation would I have sitting there? Linear, right? So b can be 0, that's okay, c can be 0, but a's got to be a real number. Okay, that's the condition. So let's take a look at how to solve quadratic equations. So I want you to do these first two, a and b at your seats, save c for when we get back together. Okay, do a and b at your seats, and let me check it out when you've got a and b done. Just put up your flag and I'll come around. Many of you, the first time around, were half right on a and b. That's very typical. It's every year. I mean, a normal person would do this. So I'm trying to turn you into abnormal people, okay? Because I want you to be math geeks, right? So when you look at z squared equals 9, automatically you're setting yourself up to get the half answer, the half right answer, if you do this. If you were taught somewhere along the line just to do this, then you say my answer is z equals 3, and you're only half right. So let's start fresh, okay? Let's start fresh. I don't want you to get fresh, but let's start fresh. All right, so number one, you look at a quadratic equation, put a little circle around that 2 to remind yourself 2 solutions. The only time you have 1 is when your answer is 0, but you will always get 2 solutions, and those solutions will be opposite of each other, or conjugates if they're complex numbers, okay? So always circle the 2 as just that little like reminder, oh, I got 2 answers here. Now, if you want a foolproof way of never getting the wrong answer, anybody want a foolproof way? One person. All right. Oh, okay, all right. The foolproof way, even though it's not the quickest, you love doing that little square root sign around stuff. Believe me, I've done this for so long, I'm going to like turn into ashes, okay? And I've done this like plea with my students, and I still can't get you not to put that square root sign above it. So I'm going to just tell you, this is foolproof. Set the equation equal to 0 and factor it. You will never forget that there's 2 answers. So if you subtract 9 from both sides, the difference between 2 perfect squares is staring at you right in the face. You get conjugate factors, z plus, you can't ask for anything easier to factor. There are your 2 answers right now, z equals -3, z equals +3. Guess what? Even when the number on the other side's negative and you add 25 to both sides, guess what? Now you get the sum of 2 perfect squares, which you know how to factor, x, 5i, 5i. Minus plus, guess what? 2 different factors, 2 different solutions. What makes that 0 when x equals -5i? What makes that 0 when x equals 5i? Okay? So if you set your equation equal to 0, you will either get, as long as you have your squared term on this side and a constant on the right, always you'll either have to factor difference of perfect squares, boom, boom, and once you do this 5 or 6 or 7 or 10 times, sums of perfect squares, you're going to feel very comfortable going right to this factorization. Okay? Now, let me show you where you go wrong with the square root. When you write this, and this, oops, this, yeah, if you wrote that, I don't know what it would be. It'd be a big mess. When you write this, part of the problem is you've been allowed. It's not your fault. You've been allowed to write this and write this, which is not correct. Well, part of it's correct. The right-hand side's correct. When you use this symbol, the square root symbol asks to give the positive square root only. Only the positive square root. So the positive square root of 9 is 3. I agree with that. You're okay on that. We don't know right now whether z is a positive number or a negative number. The square root of z squared is not z. The square root of z squared is the absolute value of z. So if your high school teachers or the teachers prior to here taught you that when you write the square root of x squared, z squared, w squared, whatever you're doing, you put those absolute value symbols around it. Now you look at that and you say, I got 2 numbers whose distance from 0 is 3 units, +3 and -3. Then, so if you include this step and solve this equation, z could be 3 because the square root of 3 is 3, or z could be -3. Then you're okay. But if you do this, I guarantee on the next quiz, if we have another quiz before the test or on the test, you'll only get half the answer. I've seen it happen over and over and over and over and over and over again. So it's up to you. Okay. Now notice the main difference between A and B and C is that in A and B you have your squared expression, which is just a baby variable here, on one side. Nothing in front of it, nothing being added to it. When you see something like C, you want to isolate your squared expression. So you want to isolate this, get this all by itself as your first step. Isolate. So how are you going to isolate that? What would you do to both sides? I wouldn't, well, let's see, someone said add to. I would add to if it said -2 plus, right? If there was a plus or a minus. So what's the -2 doing to that expression? What's the operation between -2 and this expression? Multiply. So to undo multiplication, you divide both sides by -2. Okay, so now you get this. Okay, so what do most students do? They multiply that all out. X minus 7 squared, x squared minus 14x plus 49 equals 10. They subtract. They do all this work. This isn't any different than this. You have something squared. Something squared. So to undo it, you can use this property we just discovered, the square root of both sides. The square root of x minus 7, you could say, is x minus 7 without the absolute value, as long as you remember to do this on the right side. You got to put plus and minus square root of -10. Or you could have said the square root of x minus 7 is x minus 7 in absolute value, and then put this on the right side, and then solve it by setting it equal to positive square root and negative square root. Okay, so you get two equations here. You get x minus 7 equals the positive square root of 10, and you get x minus 7 equals the negative square root of 10. So to solve for x, you add 7 to both sides, and you get 7 plus the square root of 10. There's one complex number. It can't be simplified. And guess what its partner is going to look like? Almost exactly the same, but it will be minus square root of 10. Okay? These always come in pairs. If you get one answer, you always will get the second, and they look almost identical, except for one is addition and one is subtraction. Right, so the key here is dividing both sides by -2 first. And if you wanted to, you could square this all out and do it the other way and use the quadratic formula. I'm just trying to show you how to do it more quickly. All right. Now the quadratic formula uses the, before we get to the quadratic formula, everything we've done with factoring uses this idea, and we've played with this several times this semester. If we can factor a quantity, an expression on the left-hand side, and set it equal to 0, then we know either A is 0 or B is 0. We've used that quite a bit. All right, so if we were to do this, if we were to solve these quadratic equations, notice how these quadratic equations are different than the first three we looked at. This one doesn't have a constant term. Well, you could argue that 0 is a constant, but notice we now have our x term. So the only way you can factor this, what's on the palm of my hand? It's erased now. I have taken a shower since last week. What's on the palm of my hand? You forgot? Come on. GCF. So to factor this, don't forget, GCF is your favorite friend. How do I factor x squared plus x? What's common to both terms? X. So you factor out an x, and you get x plus 1 equals 0. Now you have your A times B. You have your x times x plus 1. You set each factor equal to 0. Once you do x equal to 0, boom, you're done. There's no work. X is 0. Or x plus 1 equals 0. One step tells you x equals -1. So there are my two answers to that quadratic equation. All right. The big faux pas here is students divide both sides by x. And you'll always lose one of your solutions when you do that. If you divide both sides by x, you'll just get x plus 1 equals 0. So you've lost one of your solutions, and you're also dividing both sides by 0, which is really not a good thing to do. So factor, factor, factor. How do we factor this? X squared plus 11x plus 24. What two factors will give me that expression on the left-hand side? X plus 8, x plus 3, x equals negative 8, x equals negative 3. Done. So factoring, if factoring isn't something that's like god-awful for you, it really can be a very quick solution. And now, how do we factor C? I hope you have this like in your toolkit. We have the difference of two perfect squares. So what do my factors look like? X minus 7, x plus 7. So my answers are x equals plus and minus 7. So factoring is another technique for solving quadratic equations. But not all expressions like come nice like this for you, nice and friendly. We can get things that we can't factor, and therefore the last technique, using the quadratic equation, can be used for any quadratic equation, no matter what it looks like. So let's take a look at the quadratic formula. So some students have trouble remembering these formulas. And why do we remember when we're really little the ABCs? Because it's to a melody. Now I had this wonderful little melody that has stopped working. It was right here. And so we put the quadratic equation to Pop Goes the Weasel. All right? I am, and then we're all going to sing. So here's what the math version looks like. So this is what we're going to sing. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. All right. So I went to YouTube since as you saw, I was trying to get this to play. It didn't work. I thought I did find something. So this is the best I can do. So for those of you not familiar, some people aren't born in this country and they don't know this song. So here's the tune. This is the best I could do. It's not as good as my original one. Oh no, I don't want it to, see, now it's going on. I just want that first verse. So did anybody notice where it starts? All right. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. I can never get that high. Okay, so let's go back. Now, nobody's going to notice that you're singing because we're all going to sing together. You've got the lyrics right there in front of you. Ready? 1, 2, 3. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Yes, and guess what? You will be singing this in the shower, and it happens. And the students that never sing always come back to me the next class and say, I can't get that song out of my head. All right, so I will promise you, if you sing this little melody to yourself a couple of times, you will never forget the quadratic equation, and you'll always have it at your fingertips at your next cocktail party. Okay, so let's suppose we wanted to solve that quadratic equation. I would not use the quadratic formula on this. Why wouldn't I use the quadratic formula on this? Because I can factor it. But if you can factor something, the answers to your quadratic equation will be rational numbers. They'll be nice and friendly. They won't be yucky, like complex numbers. I'm not going to do that one for you. I don't really know how this one's going to end up. So the first thing I would do is you have to set your quadratic equation equal to 0 in order to use your quadratic formula. The quadratic formula finds the value of x that makes that true. So first you identify what a, b, and c are once you've got it in the form of setting it equal to 0. So let's see, a here is the number 5, b is negative 20 because there's a subtraction in front of it, and c is 6. So now I go to my quadratic formula, x equals negative b plus or minus the square root. If b is negative, you've got to put it in parentheses, because negative 20 parentheses square, this thing does not equal this thing. They're two different numbers. So Whenever b is negative, put it in parentheses, minus 4ac all over 2a. All right, now it's really from here like arithmetic, putting things together, and sometimes this is the hardest part for you. You can get there. So let's see what we get. Negative 5 plus or minus. Negative 20 square is what? A is 5. Did I screw up somewhere? Oh, thank you. Oh, yeah, I'm really messing up here. Huh. Wow. Thank you. So B is negative 20. So the opposite of B should be out here, 20. Thanks. See how I screwed up? I wish I could, maybe I could factor that and then I wouldn't have screwed up. All right, where else did I screw up? Oh, the bottom's 2 times 5. You know what I did? I put 10 in because I already did the 2 times 5 and called it 10. All right, stay in the present, Linda. Minus what? 20 times 6 is 120 all over 10. So part of getting the answer is just simplification with these radicals. 20 plus or minus, so we get what? 400 minus 120 is 280? Is that right? 280? 400 minus 120? Okay, 280 all over 10. So here are my two answers right here. X equals 20 plus or minus plus the square root of 280 all over 10, and 20 minus the square root of 280 all over 10. But I'm not done. If you wrote it like that, you get it marked wrong because you have to simplify that. 4 goes in there. I'm sure something bigger than 4 goes in there. Huh? 2 over 1. 2 over 1. Okay, so let's see. 4 goes into the square root of 280 is the square root of 4 times the square root of 70. 4 times 70. Square root of 4 is what? 2. All right, so we get x equals 20 plus 2 square roots of 70 all over 10, plus or minus. And now if you want, you can break this up and say 20 over 10 plus or minus 2 square roots of 70 all over 10. This is one big fat 2 right here. And this is square root of 70 over 5 when you reduce this. Okay, so you get either 2 plus or minus square root of 70, or you say this. 2 goes into 10 5 times, 2 goes into this 10 times, 2 goes into this once, and you can also write it like this. Okay, sorry we didn't have time to work problems, but let me point out you have a worksheet with some problems. So if you want to see the types of things, we can spend a little time on Wednesday working on those at the beginning of class if you want, if you need help with them.